orthogonal decomposition theorem and do some calculations today. And I bet we're also going to get to the next section, I think, the Gram-Schmidt decomposition. So there's homework due next week. The last homework assignment is due Wednesday. And it includes one problem from 6.4 also. So I hope we get to that today. I'll hand out the 6.4 handouts. The explanation of that is totally written out on the handout, but I think it's okay to have that on the homework that's due Wednesday, because even if we're still talking about it on Monday, you'll get it. You'll get that down. You'll see that problem. It's not a super tricky thing. And okay, so this, we got to get used to this formula here of y being y hat plus z. For whatever reason, this is the notation our textbook likes to use, where so this y is a vector in Rn, and W is a subspace. So we start out with Rn and a subspace W. We pull a vector out of Rn, and we call this, we're decomposing it, or we're describing it as a sum of two other vectors. So y hat is going to be in W, and the z is going to be in W, the perpendicular complement to W. And y hat, we have this formula for this. I'm not going to rewrite the formula on the board, but you're going to have to know that formula. Right here it is. And my feeling is if you know one term of that formula, you'll be able to handle this whole business. And it looks just like the formula from the previous section, because basically in the previous section, we were choosing W to be a one-dimensional subspace. So it had a basis of one vector, and this whole expression was, we weren't calling it the orthogonal decomposition yet, but we were getting just one term. Now, for a multi-dimensional subspace, we're going to have more terms. And I know we went through this argument already. So I'm just going to turn the page, because I think we ended at the end of the proof. And y hat is called the orthogonal projection of y onto W. And so another notation that's used for our y hat is it's the same as PROJ, the projection onto the subspace W of the vector y. Okay, so that's equal to y hat, and all this notation that we're juggling around. And okay, I think maybe so we can do this problem. I'm going to turn the projector off so I have lots of room. What we're going to do is we're going to verify that the two given u1, u2 vectors are orthogonal. That'll be quick. And then we're going to express y as the sum of a vector in W and a vector in W perp. So we're just going to go through that calculation. Let's turn this off. So our exercise. So W1 is 2, 0, negative 1. I'm sorry, not W1. U1 is 2, 0, negative 1. U2 is 1, 3, 2. Our y is negative 1, negative 4, 0. So these are all vectors in R3. All R vectors in R3. What we're calling W here, W is the span of U1 in U2. So a 2, dimensional subspace of R3. And I suspect Y is probably not in W, but we don't know that for sure. Doesn't really matter for this calculation, but I think it probably isn't. And so step A, verify that U1 and U2 are orthogonal. How do we do that? Dot product. Yep. All we got to do is U1 dot U2 is 2 times 1 plus 0 times 3 plus negative 1 times 2. And I hope that's 0. Thus, U1 and U2 are orthogonal. And remember that automatically means they are linearly dependent. Thus, they are also linearly independent, say. And so U1 in U2 is a basis for W. I guess we actually don't really know for certain until that point that we're two-dimensional, right? We got to verify that they really are a basis. Okay, part B. So we're going to express Y as this Y hat plus Z. And Y hat is going to be a linear combination of the vectors U1 and U2. So here's where our formula kicks in. It's Y dotted with U1 over U1 dotted with U1. So that's all a scalar times the vector U1 plus Y dotted with U2 over U2 dotted with itself times the vector U2. So that's the formula from the previous page being applied to this problem. And so what do we get? We get I'm just going to do some calculations here. U1 dot U1 is going to be 5. U2 dotted with U2, without writing out the details, is 1 plus 9 plus 4 is 14. We also need Y dotted with U1. So Y dotted with U1 is going to be just negative 2. We need Y dotted with U2. So this dotted with that is negative 13. And so our Y hat is going to be negative 2 over 5 times U1 minus 13 over 14 times U2. I think I have ugly fractions here. And I think this is just a case where I was lazy making up my problem and picked any old vectors, so the numbers come out to be awful. Ugh. They really do come out to be awful. Yeah, so I can do this to myself, but not to you. Negative 121/70ths, negative 195/70ths, negative 102/70ths. Okay, got to make up a better example here. There's my Y hat vector. So I have a common denominator of 14 and 5 from 14 and 5. 14 times 5, that's where the 70 comes from. All right, and then we need z. And the way we're always going to get z is we're just going to take y minus y hat. So our little old -1, 0 minus, I don't even feel like writing that again, right? And that difference turns out to be 51/70. Oh, I'm so glad I brought my notes. So what we can say is y is now equal to this -121/70, -195/70, -102/70, plus 51/70, -85/70, 102/70. And like, why would anybody care? This vector should be in W, and it's got to be right, because it's a linear combination of U1 and U2. It's a linear combination of the basis vectors, so of course it's in W. And then this vector should be in W perp. So z dot U1 should be 0, and z dot U2 should also be 0. And I'm not going to, maybe I'll just think about U1, z dotted with U1. I have to take 2 times this fraction, which is 102/70, minus this fraction is 0. So, okay, I did z dot U1. You can do z dot U2 because it's more complicated. Okay, so that's just the point of that exercise. All right. So don't panic. I can't give you that messy because of a fraction issue, because I would not want to correct it. All right, we're going to go back to projection. I'm just gonna try to draw a picture while we wait for the projector to come back on. So, that's closest point in W to Y. So this just formalizes what I was just kind of saying to you intuitively in that picture. So how would we write this out in symbols? And so let's see if we can follow this symbolism. I'm saying if V is any other vector in W, so V is different from Y hat, then the distance between Y and Y hat, that's the shortest distance, has to be less than the distance between Y and V. What surprises me a little bit about this, I don't know. Is there anything surprising in this statement? I would wonder if I were a student, like maybe there's another point that's the same distance. Like we are saying there's just one point that's closest, Y hat, one vector that's closest, and all the other vectors, any vector that's different, has to be further away. So there's only one closest point. So you might think as we go through this argument, why couldn't there be two, maybe? And there can't. So in our notation, so I move this up a little higher, the distance between Y and Y hat, we just denote with these double bars around the difference, Y minus Y hat. That's actually our definition of distance between those two vectors. And it agrees totally with your definitions of distance in R2 and R3 that you've already learned. That's the same thing as our Z vector. Okay? So you could think of it as just the length of the Z vector. So you actually, if we could draw the arrows, if we could use our parallel movement of arrows, you can imagine a copy of the Z arrow pointing upward right in that position, right, in the arrow notation. And so the length of Z is always less than the length of Y minus V. So proof. Let V be in W, V different from Y hat, okay? So then Y hat minus V is in W. Y hat minus V, at least its length can be visualized as that distance, all right, from Y hat to V. Y hat minus V is in W. Y minus Y hat is in W perp. That's same as our previous Z. Thus, Y minus Y hat is perpendicular or orthogonal to Y hat minus V. This difference is perpendicular to this difference. I mean, there's orthogonality there. That's the way we set this whole thing up. And so trickiness here, observe that Y minus V could be written in the following way. So we're artificially throwing the Y hat in here. If you write Y minus Y hat plus Y hat minus V, that just simplifies to Y minus V. And so by our Pythagorean theorem that we talked about just a day or so ago, a couple days, we can say the following. So this picture here is really a little slightly neater version than what I wrote on the board. And you really do have a right triangle situation here. And so we can say the square of Y minus V, so this distance squared, has to equal the sum of the squares of the two legs of that right triangle, right? And when I say must be positive, I mean, what I'm trying to say is cannot be 0, this term, because we said Y hat and V were different. If Y hat and V are different, this must be a non-zero positive number, which means if you remove it from the equation, this quantity is absolutely greater than that quantity, not possibly equal. And these are squares now. Now, I'm going to take square root of both sides, and you've got to be careful with that sometimes. But as long as you have positive quantities, if you have the squares, if you have an inequality of the squares of two positive quantities, when you go to those quantities themselves or take square roots, this inequality is preserved as long as they were positive in the first place. And that's the result. That kind of proves the statement of the theorem. Let's turn the page. Oh, and we got another problem to do. So I think I'm going to put the screen up again and turn it off. Let's actually find the distance from Y to And this is not the same u1 and u2 as in the previous problem. So thankfully, we can say goodbye to the ugly fraction problem. So let's just clean everything off and get our exercise on the board. So distance from y, which is 1 to negative 5, to w, which is equal to the span, so I'm paraphrasing the statement a little bit here, of u1 and u2, where u1 is 1, 0, 1, and u2 is 1, 1, negative 1. So, you know where this is headed. We want, in our whole scheme of things, we're going to work with y hat plus z again, where y hat is in w. I didn't use the capital W on the handout, but I'm introducing that here, the span of those two. Call the subspace W. Z is in W perp, okay, the perpendicular complement of W. But what do we want here to get distance? Yeah, we want the length of Z, right? So just realize that. We want the length of the Z vector. So how do we get the length of Z? We get Z. How do we get Z? We got to get y hat first. So see the chain of what we need. We can't just jump right to the length of Z here. First, find y hat, the projection of y onto W, and y hat, which is going to be y dotted with u1 over u1 dotted with u1, u1, plus y dotted with u2 over u2 dotted with u2 times u2. And of course, if W were a three-dimensional subspace, if there were a u1, u2, and u3, and there would be three terms to that expression for y hat. Four-dimensional would have four terms. I guess we should verify that u1 and u2 are orthogonal. Or we can't even do this. And if they're not, I'm in big trouble. So what is u1 dotted with u2 is 0, right? Otherwise, we can't do this. If they're not orthogonal, this process doesn't happen. So yes, they are. Ooh. And now it's just this mess of dot products that we got to calculate again. u1 dotted with u1 is 2. u2 dotted with u2 is going to be 3. Y dotted with u1 is negative 4. Y dotted with u2, tell me if I'm making a mistake, y dotted with u2 is 3 plus 5 is 8, positive 8. So our y hat is going to be negative 4/2 u1 plus 8/3 u2. Oh, 8/3. Oh, well. Could be worse. So I'm happy to get thirds. And these guys add up to 2/3, 8/3, negative 14/3. All right. Now we need z. Z is equal to y minus the y hat. All right. So we subtract y minus the vector we just found to get z. So we're going from y hat, which sits in w, to z, which is a vector that's perpendicular orthogonal. I don't know. I always say perpendicular. Yeah? Question? No? We're good? Yeah, I think you guys will like this stuff. 1, 2, negative 5, minus 2/3, 8/3, negative 14/3. And I'm going to try to do that in my head. I get 1/3, negative 2/3, negative 1/3. Okay. So there's z. And along the way, if you just want to wonder if you're on the right track, it's a good sign if z dot u1 is 0 and z dot u2 is also 0, right? There's a problem if that's not working out. You made a mistake. And I think you can see that's true here. Okay. Now we're almost done. We're not done yet, though. We need the distance is the length of z, which is the square root of 1/3 squared plus negative 2/3 squared plus negative 1/3 squared. And I know my pre-calculus class would say, can we just leave it like that, Mr. P? Because you don't know what you're going to see out of this from my pre-calculus class. You don't know what's going to happen. So what do we got? Square root of 6/9, so square root of 6/3. Is that right? Or square root of 2/3, I don't know. I don't have any rule about what the official simplified form is, so whatever you want. Okay, boom. Question, or I think you'll see when you read this. It's a pretty straightforward process, I think. So we got time to start talking about Gram-Schmidt, because I think we're to the end of the 6.3 handout, so 6.4. Gram-Schmidt process. Every once in a while, I have these dreams about when I was back in undergraduate school, and I hear those words, Gram-Schmidt, in my dreams. Nightmares? Oh, no. There's more. Everybody has one, right? Yeah. So the Gram-Schmidt process is now, it's one technique. And we're basically going to go through one example on the handout. And you will have to, I think there's just one example of this that you have to turn in on the homework that's due next Wednesday. And this is definitely something you're going to have to do on our fourth exam, which I think is the Friday after Thanksgiving holiday. We got one more exam before the final. And it's very much a step-by-step process, and yet it's hard to turn into a single formula, all right? So try not to think of it as a single formula. If you get the idea of some of this geometry of what we've been doing, it's going to be a lot easier to work through these steps. So what's this all about? The Gram-Schmidt process is this. Given any basis for a non-zero subspace W of Rn, so I call it x1 through xp. This is a basis, so they got to be linearly independent vectors. And, of course, they span their span, so they're a basis for the subspace that they span, but they're not necessarily orthogonal to each other. Gram-Schmidt is about turning any old basis into a new basis of vectors that are orthogonal to each other, mutually orthogonal. So any basis can be turned into an orthogonal basis. Very classical result. And, of course, the number of vectors in the new basis is the same, right? Because if the dimension's p for the subspace, we better end up with p vectors. And this is called Gram-Schmidt process. And we're going to jump right into an exercise here that maybe I'll write some down too, but I have the whole thing written out on the handout for some reason. So let's just try to work from the handout, and if we feel the need to write things down, we will. So I'm starting out with x1, x2, x3. So this is a basis for a subspace of R4. So we're looking at a three-dimensional subspace of R4, and that's the kind of thing I love to think about. So we have a copy of R3 sitting in R4. We have a copy of space sitting in one little teeny tiny corner. It's one little slice of R4, right? Just like a two-dimensional plane is a slice of R3. A three-dimensional subspace is just one slice of R4. And note, it's given that they are linearly independent. We don't have to show that here. And it's not too hard to show that they're, like, for our final exam now, you would know how to show that these three are linearly independent. And maybe it's worth noting, too, I don't think they're orthogonal. If I take the dot product of x1 and x2, I get 2, right? I don't get 0. Or if I take x2 dotted with x3, I get 2. And if I take x1 dotted with x3, I get 1. So they're not orthogonal. They'd be orthogonal if all those dot products were 0. And so we're going to find an orthogonal basis by working from these x1, x2, x3. All right, so we got to find a v1, v2, and a v3. If I gave you 1/3 credit for finding v1, 1/3 credit for v2, 1/3 for v3, it's like everybody gets 1/3 credit because v1 is x1. So you all know how to find v1. Don't work too hard finding v1. Basically, you just pick one to be your starter. All right? All right, so we're just going to let v1 be x1. We're done. We found our v1. Step 1 is very straightforward. Step 2 now, what we're going to do is we're going to use x2 to find a different vector, but we're not going to use x2. All right? So just think of the logic of this here. What you're going to do is first find the projection of x2 onto v1. So we're using this formula with a one-dimensional case, right? x2 dotted with v1, v1 times v1. So that's, I went ahead and did all those dot products ahead of time, so it's 2/3, times the v1 vector, but that's the same as x1, 1, 1, 1, 0. Okay? So we project x2 onto our first vector. Now, that's not what we want, right? Because that's a scalar multiple of our first basis vector. We already have that dimension. We want a dimension perpendicular, orthogonal to that, right? So what we're going to do is go back to x2, take x2 minus that projection, okay? So x2 minus the projection of x2 onto v1. That should make sense. That's kind of like getting a z out of it in a way. And it's going to give us, again, here's my 0, 1, 1, 1. That's x2, not x1. So you're going to have to work on keeping the details straight here. This is x2 minus what we just calculated. And here's what I get. Negative 2/3, 1/3, 1/3, 1. Okay. So I know this vector is going to be perpendicular or orthogonal to our v1 vector. And this is going to be our v2. All right. So we got our second one. You can always check along the way. Take what I circled here, dotted with our v1, what I circled there. The dot product better be 0, or you're in trouble, right? So we got our second one. So we project onto the second one, but we don't use that projection. I mean, we project onto the second one onto the first, and then we subtract our second minus the projection to get our second basis vector. And now the third step, which I guess I just start here on this bottom of the page. Okay. So now we got a v1 and a v2 already, right? We got two basis vectors, two orthogonal basis vectors. We're going to take our third vector and we're going to project onto both v1 and v2. So there's this calculation of x3 dotted with v1, v1 dotted by. There's that formula we see over and over again. I'm projecting x3 onto v1 and onto v2. Okay, so it's just a calculation. We get that vector, turn the page. And now this is something like a little bit different, but I'm going to take x3 minus the projection of x3 onto v1 and the projection of x3 onto v2. Or, I mean, you could say it's just easier to talk about it this way, but actually, if I add those two together, I'm really looking at the projection onto the subspace spanned by v1 and v2, right? So these two vectors, the sum of these two is the subspace spanned by v1 and v2. When I take x3 minus that, I'm getting a new vector perpendicular to the subspace spanned by v1 and v2, okay? So it gets a little bit more complicated, right? But the pattern of the formula is easier to see, I think, if we write it in this way. So it's x3 minus that one projection minus the other. And there's our third vector for the orthogonal basis. All right? And again, we can check. I can take the dot product of this with each of the two circled vectors on the previous page, and they should be 0, and then I'm feeling pretty good about it. So you have no reason to turn in a wrong answer, because it's so easy to check your answers, right? You can say, I tried and I didn't get it, but you shouldn't think you got it when it's the wrong answer, right? Because we can verify that orthogonality. Now, I say, what if we had a fourth step? You know, what if we were dealing with a basis of 4 vectors? The pattern, I think, is easier to see if I write this down one more time. And I don't want to cover that up. If we had to do this again, we would take our fourth vector, our fourth basis vector, and subtract the projections of that fourth vector onto the v1, the v2, and the v3, the first 3 of the orthogonal basis vectors in our answer that we found, right? And then there might be another step or another step. Well, I can't ask you one. That's too complicated. Now, that's called Theorem 11. Is that process in the book. And there's a general formula on page 357, I say. But I hate that general formula because it's just so abstract. It's got too many dots in it, and it's got like n, and it tries to, I think you just want to see how this process builds from one step to the next. Each succeeding step is a little bit more complicated than the preceding one. And that's the Gram-Schmidt process. And what else do we have to say? Oh, just a note here that as you build up the new basis, I think it's just, to me, it's just interesting to see that the span of v1 is the same as the span of x1, because v1 is x1. The span of v1, v2 So the subspace spanned by v1 and v2 is the same as the subspace spanned by x1 and x2, and so on and so forth as you work through Gram-Schmidt. And that's all I was going to do about Gram-Schmidt. No. Oh, no, there's more. Oops. Oh, shoot, I thought I was going to break the world record and get into another section in 1 hour. But we got a little bit more we got to say. This is just discussion. The Gram-Schmidt process can be used to find an orthonormal basis. Orthonormal means orthogonal vectors that are also unit vectors. I'm not going to ask you to find an orthonormal basis, okay? And it's very easy to do. And there are different techniques, but you can just find your orthogonal basis, and then what you can do is you just take each one of the vectors you got and divide by its magnitude to normalize it, or to get unit length, right? So we got v1, v2, v3. I could calculate the length of each one of those. I could multiply each one by 1 over its length, and then I get what's called an orthonormal basis. So I'm not going to ask you to do this because it's basically just a very tedious exercise by hand, but it just always can fall out. And often what folks really want for calculations is an orthonormal basis. Theorem, every finite dimensional vector space has an orthogonal basis, and in fact has an orthonormal basis. That falls out of this process. This process shows how we can convert any basis to orthogonal and also orthonormal. We're going to skip QR factorization in that section. So if you're reading along, you don't have to read that section. And now we are to the end of the handout. And I want to finish today just by giving you the next sheet since I have it ready. So you'll be OK with Gram-Schmidt, but you have to practice it, and you are going to be asked to do that on an exam and a final. And if it makes no sense whatsoever on Monday, just come back and tell me we got to do another example. But usually everybody's OK with that once they see that one detailed example from the handout. OK, so I guess I'll flash this up on the screen. I don't think I learned this next topic when I took linear algebra as a student. We went off in other directions. All the emphasis was on differential equations. And I just love this example. And I just want to introduce it, and then we'll quit for today. Least squares problems, they're called. But here, just think of the wording here, what we're talking about. Sometimes in applications, you get an application and you're trying to solve a matrix equation. AX equals B. And what if it has no solution? Well, do you give up? Do you say, well, forget it, impossible problem? But it may be relevant to find x so that AX is as close as possible to B. So what if you could find an AX that's approximately equal to B? All right? And that's really what this section is all about. What does it mean to approximate? And what does it mean to find the best possible approximation, right? Like, how do we know we have a good approximation or a bad approximation? So note that if AX equals B, okay, then we can write B minus AX equals 0. All right, and B minus AX is a vector, right? A column vector. A is a m by n matrix. I think dimension could be anything here. But once we multiply by x, we have a vector. B is a vector. So this difference is a vector. So you can talk about the length of that vector. The length of that vector is 0. Now, if AX is close to B, we're going to build off this idea of length. So suppose AX is not equal to B, but just close to B for some vector x. Then the length of B minus AX is small. So we're going to try to find x so that B minus AX is as small as possible. And let's just read. Yeah, we got 1 minute, so let's just read this statement. So if A is an m by m matrix, B is an Rm, x is an R, then x hat in Rn is called a least squares solution to AX equals B if the following is true. And it's kind of like that inequality we just looked at, but we do have less than or equal to here. If the length of B minus AX hat is less than or equal to the length of B minus AX for all x in Rn. And a given matrix could possibly have just one, a uniquely square solution, or possibly infinitely many. So x hat is what we're going to be looking for next week, and we'll stop now. Okay?